Okay, here we have a fairly complex multivariable calculus question, and it asks us to set up and solve an integral using change of variables. So we've got an integral over the region R, and the integrand is 1 over x squared dx dy, and we're told to use u equals x squared minus y squared and v equals y over x to use the change of variables, solve the integral, and R is the region in the first quadrant under y equals 1 over x, and right of, that should be right of x squared minus y squared equals 1. Okay, so a lot going on there. I'm going to just very quickly start by drawing a very rough sketch of what's going on here. So we know what y equals 1 over x looks like. I'm going to try and draw the region of R. 1 over x looks like that. Y equals 1 over x. And this function here, if we don't remember, x squared minus y squared equals 1, that's a hyperbola, and if we're just in the first quadrant, it's a hyperbola that sort of starts at the point 1, 0 and goes out like this. Right, so we can see there's a point of intersection here, there's a starting point here of 0, 1, and you can see as x in the red here goes to infinity, y is going to 0. So that's all well and good. Now we've got to change, there's two big parts to this change of variables method. One, we've got to figure out our limits or our boundaries on our integrals. And then we have to use the Jacobian in this case, because it's not polar coordinates or anything, we don't know it off by heart. We've got to use the Jacobian matrix to be able to figure out our, the integrand that we're actually going to integrate over. So how does that work? Well, first I would go to the points of intersection to actually figure out the boundaries of our region. So I've already got the point 0, 1. That's really easy. And in terms of if we were to map that 0 to 1, this is x, y. If we were to map that to uv, you can just sub it into any of the values, any of the equations, and I'm going to sub it into, I'm sorry, that's 1, 0. The point 1, 0, not 0, 1. There we go. So this is the point. Let me erase that so we don't get too messy here. Okay. So that's the point 1, 0, as you know. And so if we map a point x, y to the point uv, we've got 1, 0. Plug that in, say, to v, where it's y over x, and that will be, v will be 0, and u will be 1 minus 0, which is 1. So it's the exact same point, which is nice. So we know that's sort of a starting point for us, where u is 1 and v is 0. And we know that's going to be the lower bound of u, because you can just look at the u formula, and we know that x is getting bigger and bigger and bigger, and y is getting smaller as we go out further, so u is only going to get bigger than 1. Okay, perfect. We also need to find this other point of intersection. That's going to be a little bit more difficult, but let's see if we can do it, because that's going to be the maximum value that v hits. So let's see if we can just set, we've got we've got our two equations, y equals 1 over x, and it intersects with x squared minus y squared equals 1. So you can do it any number of ways, but I'm going to do it by squaring y equals 1 over x. I'm going to say y squared equals 1 over x squared. Just squaring both sides of that equation. Then I can substitute that in for y squared in my second equation. So I had x squared minus y squared equals 1. So I'm now going to say this is x squared minus 1 over x squared equals 1. Multiply everything by x squared, and we get x to the 4 minus 1 equals x squared. Everything to one side, we get x to the 4 minus x squared minus 1 equals 0. And this is a quadratic in terms of x squared. So I know it's x to the 4, but if we were to set m equal to x squared or something, we could write this as a quadratic, and the variable would be x squared. So I'm going to use the quadratic formula, setting x squared equal to my root. Negative b is 1 plus or minus the square root of b squared, so 1 squared minus 4 times negative 1 is 4, so root 5 all over 2. Perfect. So I know that x squared equals 1 plus or minus root 5 over 2. So I know that x equals plus or minus the square root of that whole thing. Fair enough. Now, let's remember what the y value is here, right? This is the point x and 1 over x. Okay? So we know that we know x is the square root of that, and here's the tricky part. That's great that this is x and 1 over x, but we ultimately want to figure out what the v value is at this point. And we know v equals y over x, which I'm just going to break this out so it's easier to see. This is y times 1 over x. And at this same point, we know that's on the curve 1 over x. Look, right here we said the y coordinate is actually 1 over x. So I can replace that y with 1 over x times the 1 over x. So we've got 1 over x squared. So we know our v value is actually going to 1 over x squared, which is just the reciprocal of this guy. So it's 2 over 1 plus or minus root 5. Okay, so a little bit of a trick there, but it really helps to sort of simplify to determine what v is. So I've now got my v value we know is going from 0 to this. So my v limit is going from 0 to 2 over 1 plus or minus root 5. And I know my u value is going from 1, because it's sort of starting here, and it's going to the right anywhere it hits this curve. So what we want is to be able to hit that curve in terms of v. So how do we do that? Well, that curve we know is y equals 1 over x. And we know that, and subbing that into my v equation, I know v equals y over x. So that's 1 over x, which equals 1 over x squared. But we also need to figure out how this falls into the u equation. So u equals x squared minus y squared. So it's this 1 over x squared. So u equals x squared minus 1 over x squared. And we just said that v is equal to 1 over x squared. So u in terms of v, so I'm basically taking this and putting it in here. So this becomes 1 over v minus v. Therefore my u goes from 1 to 1 over v minus v, basically anywhere it hits that curve, right? All the horizontal lines. So I'm going to circle that piece, because those are going to be my limits. And then I'm going to erase everything, and we can figure out the Jacobian part. Okay, so I've drawn sort of our normal formula. We're going from the x, y, rectangular variables to the change of variables in terms of u and v. And this is what it normally looks like. dx dy becomes the Jacobian of the x, the derivative of x with respect to u, and the derivative of y with respect to v, etc. So always dx by du and dx by dv and dy by du and dy by dv. Normally that's how it is. However, in this particular question, here's where the real trick comes in, is it's going to be very difficult to explicitly solve for x or y in terms of just u and v based on these two equations. Because one has an x squared and one has an x and the other has a y squared and the other has a y, it's going to, again, be very difficult to explicitly solve for x or y just in terms of u and v. However, u and v are already given to us in in terms of x and y. So we can flip this on its head and actually solve for our Jacobian of u and v with respect to x and y. And we'll see what we get there. It'll be, so u by x, so, well, I'll write it all out. So du by dx, not du, it's the partial derivative, and du by dy, and dv by dx, sorry, there shouldn't be a line there, and dv by dy. So all those partial derivatives and take the determinant. So partial derivative of u with respect to x is just 2x, with respect to y is minus 2x, v with respect to x is negative y over x squared. It took me a second. And with respect to y, it's just 1 over x. Do the determinant, and we get 2 minus 2y over x. Okay, and we know, now we still know we're going to be differentiating with respect to u and v. In fact, I've got that here. So I don't want this y over x in my equation, so I want 2 minus 2v. Perfect. So I've got my Jacobian piece. Now we just need to actually put it into the integral, and note that we did uv over xy. Therefore, we're actually going to not write this, but we're going to divide this by uv over xy, which is our 2 minus 2v that we just found. Okay? So, I've got my two integrals. We've got 1 over x squared, and we're going to have to do something about that because we don't want any x's or y's in there because we're not differentiating with that. And we've got du dv over 2 minus 2v. Sorry, I just saw that this was actually supposed to be a y. I think I said y, but wrote x. So when we multiply that, this actually becomes minus 2y squared over x squared, which is minus 2v squared. That's better. Which is 2 into 1 minus v squared. Okay, so we're getting there. So again, I've written this under du by dv, so 2 into 1 minus v squared can go right there. So we're getting there. We still now have an x squared and a v squared. That's not very good. We definitely want to get rid of that x squared. So how can we think of 1 minus v squared? Well, we know that v squared is y squared over x squared. So what if we took our original u equation and we said, okay, I know that u equals x squared minus y squared. What if I divided everything by x squared? So I get u over x squared equals 1 minus y squared over x squared, which is v squared, right? So I can say u over x squared equals 1 minus v squared. So this whole thing can be replaced by u over x squared. So u over x squared, and there's our magic bullet because the x squareds then cancel. So our overall integral, and I'm going to put the limits in right away, is du dv over 2u, which is very nice and easy to integrate. Now, thinking about what order we're going to integrate with respect to, if we look at our limits that we found before, u is in terms of v, and then v has constant limits, so we're going to do u first. So my inside limits will be from 1 to 1 over v minus v. And our outside limits will be 0 to, we know this is positive, so it's going to be 2 over 1 plus root 5. That's going to be our top limit. Not the nicest, but you can see how that works. You can bring a 1/2 out, and then this is just ln u, ln absolute value of u, from 1 to 1 over v minus v. So this is just going to become ln of 1 over v minus v. And then you'll integrate that with respect to v. dv 1/2 is out front, and from 0 to that messy value, I'll call it b. Not going to be the greatest integral from there, but it would probably ask you, even though it said solve up here, it would really only ask you to simplify this and set it up. So the difficult part was figuring out the limits, and of course we know that always drawing a diagram of our original region helps, so that we can just change the variables and figure out where the main points go from xy to uv. And then the Jacobian was actually tricky here because we couldn't isolate x or y. We had to do it with u and v isolated in terms of x and y. So we had to make sure we divided by our Jacobian instead of multiplied. Tough question, but hopefully you're able to follow all those steps. A lot of little algebra pieces that are needed to sort of make it simplified, but if you stick with it, hopefully it makes sense.